Okay, I think we're ready to get started. My name is Charles Zona, and I would like to welcome everyone to today's Macron Group webinar. Our presenter is Nicole Groschan. Nicole is a cleanroom microscopist with Macron Associates, and she is going to talk to us about how to calibrate your microscope using the microscope's Eyepiece reticle and a stage micrometer so that you can obtain true, correct particle measurements. This webinar is being recorded and will be available on the Macron Group website under the Webinars tab. And now I will hand the program over to Nicole.
Thank you for the introduction, Charles. Good afternoon, everyone. Thank you for taking the time out of your day to join us. If you have any questions, there will be a chance to ask them at the end. So let's get started. So what is micrometry? It is the measuring of linear distance, such as width and length, of microscopic samples. But before we can accurately report particle dimensions, we need to calibrate our microscope. There are three major components of calibration. First, you will want to focus your eyepiece reticle to your eyesight. The benefit in doing so is that your eyes may differ in acuity, so focusing your eyepieces separately from one another will prevent squinting, eye strain, tension, and even headaches. Second, you will want to find true magnification. Calculating true magnification for each click stop will give perspective to the images you take. Saying an image was taken at click stop 4 does not mean much to the viewer, since click stops vary from microscope to microscope. But saying the image was taken at 60 magnification is important. And lastly, you will want to calibrate your click stops to a certified stage micrometer. Doing so will allow you to measure samples accurately. Here is an image of a stage micrometer we use at Macron. We do sell them at Macron Microscopes and Accessories if you are interested in purchasing one. My contact information will be available again at the end of the presentation. And at Macron Associates, we do check our calibration annually. If the measurements are not within 5% of our original calculations, it is an indication that there might be an issue with the microscope's alignment. Today, my calculations will be using the click stops from the Nikon SMZ1270. However, the calculations I will be sharing with you in the following slides can be used for any stereo or polarized light microscope. So now we will jump into greater detail on the three steps of calibration that I had discussed. The first one being that we need to focus our eyepiece reticle. You'll want to find a sample to focus on, so something with fine features such as small typed font on a piece of paper would be a perfect example to use. Second, you will want to determine your dominant eye and place the reticle on that side. Eyepieces are usually removable and interchangeable with one another. If you have this option on your microscope, the reticle, or the scale bar, should be placed on the side of the user's dominant eye. So I have a quick exercise we can do right now to help determine your dominant eye in case you aren't sure which one is. Extend one arm out and hold the thumb of that hand in an upright position. Keeping both eyes open and focused on a distant object such as a clock, superimpose your thumb on that object. Alternately close one eye at a time. The eye that keeps your thumb directly in front of the object while the other eye is closed is your dominant eye. Here I have an image of how the eyepieces are interchangeable with one another. And the third step is to focus your dominant eye reticle. Using your dominant eye only while keeping the other eye closed, focus the eyepiece crosshairs by rotating the uppermost eye lens of the dominant eye eyepiece until the crosshairs are in focus. And the fourth and final step is to focus your non-dominant eye reticle. While closing your dominant eye, turn the diopter adjustment ring at the base of the non-dominant eye eyepiece until the sample is in sharp focus. The second component to calibrating your microscope is finding true magnification for each of your click stops. There's a 3-step calculation used to determine this. First, you will want to find the eyepiece magnification. Sometimes it will have it printed on the piece itself, other times you will need to look into the manual to find this information. Next, you multiply this number by the coaxial illumination magnification. On the Nikon, along with many other scopes, it is printed right on the front. The Nikon, for example, is a 1.5x magnification. Next, you multiply by the objective magnification, which can be found printed directly on them. It's difficult to tell from the angle in this image, however, there are two objectives here. One is in the back. The one that we'll be using for our calculations today is a 1x, the one in the back is a 1.5x, so you'll need to recalculate if you do switch out your objectives. And the final step to the calculation is multiplying by the knob magnification or click stops found printed on the side knob here. By multiplying these magnifications, you find your true microscope magnification. So now let's set up a chart to keep our calculations organized. There are 7 click stops for the Nikon, so there will be 7 different calculations. For this Nikon, the eyepiece magnification is 10, and that will remain constant for all the calculations. The coaxial illumination magnification is 1.5, and as I mentioned earlier, it is printed on the front of the scope. The objective magnification will be 1 for these calculations. If you change objectives, you need to recalculate. The knob magnification, or the click stops, are found on the knob here, and I've listed them below. When you multiply these numbers across, you find the true magnification for the microscope. It is important to keep these two numbers handy for the chart that I'll be showing you in the following slides. Now I will give a brief overview for the 5 steps in calibrating your objectives. We will go into greater detail of these steps in the following slides. First, you will want to calculate the distance of each stage micrometer division. Second, line up the micrometer with your eyepiece reticle scale. Third, count divisions and calculate size for that magnification. Fourth, increase magnification and repeat calculations for each click stop. And last, you will want to create a sizing chart to keep at your workstation. Now we will take a little closer look at each of the 5 steps. First, you will want to calculate the distance of each stage micrometer division. Observe the unit of measure of the certified stage micrometer from the units on the micrometer itself or on the certificate of analysis. Calculate the distance of each division using this formula. Total scale length divided by the number of divisions equals length of each division. Sometimes the stage micrometer will have the distance between each division noted right on it, but if you would like a thorough understanding of where these numbers come from, or would like to convert from millimeters to micrometers, knowing this formula will come in handy. Here I have an image of what a typical micrometer scale will look like. We can run through an example using the formula above. Total scale length, which is 1 millimeter, or 1,000 micrometers, divided by the number of divisions, which is 100, equals length of each division. So for the stage micrometer shown here, every division equals 10 micrometers. Moving on to the second step in calibrating your objectives. Line up the micrometer with your eyepiece reticle scale. Place the stage micrometer on the stage of the microscope and bring the scale into focus. Position the stage micrometer so that its 0 overlaps with a 0 on the eyepiece reticle scale, as I've shown here. On to the third step in calibrating your objectives. Count divisions and calculate size of a single division for that magnification. Count the number of stage micrometer divisions that match up with the largest visible number of the eyepiece reticle divisions and enter in the following equation. The number of stage micrometer divisions, and the example I have here is 100. divided by the number of eyepiece reticle divisions. And this example is dead on at 45. Times the number of microns per stage micrometer division. In step 1, we calculated this to be 10 microns, equals 1 eyepiece reticle division. So for this example, 1 eyepiece reticle division is 22 microns at 45x. Let's do another practice problem using the equation from step 3. For this example, I took an image of the scale bars at click stop 6, magnification 90. So to recap on the formula I just shared with you, the number of stage micrometer divisions, which in this example is also 100, divided by the number of eyepiece reticle divisions, in this case it's 91, times the number of microns per stage micrometer division, and this will still be 10, equals 1 eyepiece reticle division. So for this specific example, 1 division equals 11 microns at 90x. On to the 4th step of calibrating your objectives. Increase magnification and repeat calculations for each click stop. Every time you increase magnification, you will need to realign the zeros from both scales and count the divisions. Continue this process until you have calculated the size of 1 division at each magnification. Here I have some examples of what the different click stops and magnifications would look like. It's best to start at the lowest magnification and work your way up. On to the 5th and final step of calibrating your objectives. Create a sizing chart for your workstation. Instead of making calculations every time you measure a particle, create a cheat sheet to expedite your observation process. Now grab your click stop and magnification numbers from the previous calculations and start to fill them into a chart in Excel. The first row will be the length of 1 eyepiece reticle division at that click stop. You can easily expand your chart by using simple multiplication. For example, 2 divisions at 105 micrometers gives you 210 micrometers. 3 divisions gives you 315 micrometers, so on and so forth. This chart comes in handy. Say for example, if you are working at click stop 3, you can grab your chart and see that you're working at 45x. And if you find a particle that's 7 divisions long, you know that it's 154 micrometers. Now that we've completed our chart, let's practice using it. I have an image here of some particles at click stop 8, magnification 120x. Let's try to measure this particle. So it looks like it's about 8 divisions across. So if you head over to your chart, 8 divisions at 120x equals 64 microns. That's a lot easier than pulling out a calculator every single time you want to measure a particle. And that sums up how to calibrate your microscope to accurately measure particles. I have a few references and acknowledgements. I use some images and information from John Daly's Essentials of Polarized Light Microscopy, and a special thank you to Leslie Bullen, our graphic artist, for helping with photography and editing. That wraps up my presentation for today. Thank you for joining us. If you have any questions, we'll take them now. Otherwise, my contact information is listed here.
Okay, I think we're ready to start taking some questions. If you have any questions, please go ahead and type them into the questions box, and we will answer them as they come in. Looks like we have a question from Alex. Which stage micrometer do you recommend, and where can one be purchased?
Sure, there are several different kinds and you can find them listed on our website. I recommend getting in contact with one of our sales representatives from Microscopes and Accessories. They can help you determine which stage micrometer would best would be best for the type of microscope that you have and for the application you'll be using it for. There are different types, including transmitted, reflected, light, and SEM micrometers, and we sell them to anyone that will need them for a manufacturing lab, forensic lab, or a clean room.
Yeah, they're used in a lot of different environments, applications. So yeah, they have a lot of them listed on the website there, and they'll be able to help you out with that. Looks like we have a question from Louis. Should the stage micrometer be recertified? And if so, how often do you recommend doing this?
Yes, they definitely can be. They do not expire, and it is up to the user and the company's policy as to whether they need to be recertified. Recertification can be handled through Macron microscopes and accessories, though, so we'll also be able to help you with that when you need it.
Okay, I think that does it for the questions, and thanks again for everyone out there who tuned into this webinar, and we hope to see you soon at another Macron Group webinar. Thanks.